Thanks, everyone, and David and Al. It's been a fun day. So I didn't give a real title, so I forced my hosts to guess. So roughly speaking, I'm going to say something about analytic aspects of the superconformal Bootstrap. Namely for extended supersymmetry. And this title starts out very general, and then there's going to be a slow focus over the course of the talk until I'm talking about some very particular thing. Accordingly with the title, the topic is superconformal field theories with sort of a lot or lots of supersymmetry, where lots will depend on the number of dimensions in many dimensions, where many usually means more than 2 in the context of conformal field theories, but I will mostly be working in more than 3. And I won't say a whole lot about motivation, except that there's a lot of theories of this type that are interesting for various reasons that hopefully many people already think are interesting. And if not, I probably won't convince you today. There's mysterious superconformal field theories in 6 dimensions that people think have a lot to do with dualities in lower dimensional theories. N equals 4 super Yang Mills is a very interesting theory, but we don't know how to say much about it at finite coupling at finite n. There's a lot of interesting sort of isolated N equals 2 theories in 4 dimensions that, again, we don't have the tools to say a lot about in the conformal theory itself. In general, with supersymmetric theories, we can do things like study the theory at some point on the moduli space and get some picture of sort of where some mysterious point lives inside of the context of some family of theories that makes sense. But we usually don't have much to say about sort of the CFT where it lives. So the point of bringing a bootstrap philosophy to bear on this question is just to try to sort of meet the CFTs where they are and see if there's anything interesting to say. So, to set the stage, I just want to say in extremely broad terms, relative to what David was talking about this morning, in terms of sort of how the bootstrap problem looks, in particular how it looks different when you just start adding supersymmetry to the game and saying what might happen, what might work well, what might be interesting, what might not work. So the most obvious thing is that relative to a generic conformal field theory, there's new symmetry in a supersymmetric theory. There's supersymmetry. So in addition to the P's and the K's and the M's and the D, there are schematically some Q's and some S's and some R's, which are some supercharges, some special superconformal transformations, and some sort of R symmetry, where the amount of R symmetry will depend on the details, and exactly what sorts of spinorial indices these are will also depend on the details. And once I have these new ingredients in my space-time symmetry algebra, there are some immediate consequences for just how I imagine the bootstrap problem will set up. So one immediate consequence is that in some sense there are more representations of the space-time symmetry algebra. So in an ordinary conformal field theory, I have some representations that are labeled by the dimension and spin of the highest weight state, as David was saying, and there's a few special representations, which are things like conserved currents. And those are very special, and they satisfy some unitarity bounds, and then frequently, I don't have many of those in my theory. I might have some conserved currents associated to global symmetries and some a conserved stress tensor, but I'm not going to have all sorts of higher spin conserved stuff. Whereas in supersymmetric theories, instead of just having shortening conditions that have to do with sort of divergences being 0, I have some sorts of BPS representations as well, which means that I'm going to have operators that obey conditions like being annihilated by Q, which are maybe the most familiar, and also maybe some more complicated representations where there's some lower or some more complicated shortening condition having to do with the action of Q's. And so these are some super conformal primaries. They're the highest state in the whole representation. Then you act with all the Q's and all the K's and everything subject to these shortening conditions. And you get some more interesting representations which obey some BPS conditions, which means that their conformal dimensions are fixed in terms of their R symmetry and their spin. So these are going to be sort of the main feature. And in general, in sort of the work that people do on super conformal field theories, usually the existence of special representations that are protected and have conformal dimensions that are like integers or half integers does a lot of the legwork. A related fact is that we get to play with scalars more easily. So something that David, I don't know if he said it out loud, but he probably was saying it in secret, is that if there were no external circumstances stopping you in general in the Bootstrap, probably the first 4-point function that anyone would want to study would be the 4-point function of stress tensors. And well, maybe not everyone, but I think a lot of people, because that's sort of the iconic operator of the fact that you're studying a conformal field theory, or even studying some local quantum field theory. Similarly, you might want to study the 4-point functions of conserved currents, because sort of the most basic thing that you can imagine knowing about your theory is what the global symmetries are. And so having some conserved currents follows from the spectrum of global symmetries. But you pay the price in the non-supersymmetric case, because you have to study all sorts of complicated tensor structures and things that appear in the 4-point function, and it can make the numerical problem, or even just the analytic problem of setting it up, hard. So the key, one of the sort of attractive generic features of supersymmetry is that we'll frequently have the case that things like the stress tensor and conserved currents are the action of Q some number of times on some scalar operator. And so you can sort of imagine that you're going to learn what you would learn if you could only study the correlation functions of stress tensors and conserved currents without worrying about all the details and just being able to play with scalars. At a slightly more technical level, you add super to the beginning of the phrase conformal blocks, which means that you're getting some reorganization of what you would have in the ordinary CFT case, where some finite collection of representations of the conformal algebra are related by supersymmetry. And so their contribution to 4-point functions or other correlation functions will be sort of correlated. I want to point out that this, at first, doesn't seem like a huge improvement. The crossing symmetry problem in general, if you wanted to study it analytically, is hard because it's sort of an infinite dimensional problem in infinitely many unknowns. And it's hard to make sense of that, although you can do things numerically. And this is some finite dimensional improvement on that infinite dimensionally hard problem. So there will be, you can work out the details and figure out sort of how things get put together, but it's not immediately obvious that you're going to win big time by having this small reorganization. And again, related to that is that you have a special global symmetry involved in your theory, which is some R symmetry, which is slightly better than an ordinary global symmetry because the operators appearing in different R symmetry representations may be related by supersymmetry, which wouldn't be the case without supersymmetry. Okay. So how do these various extremely heuristic considerations manifest themselves at the level of the OPE? Although I will still keep things pretty heuristic. So say I want to study the 4-point function of some operators that transform in some representation that I'll call curly R of the R symmetry. And for simplicity, I'll just imagine they're scalars because I like being able to work with scalars. Well, I'm I'm going to study the 4-point function in principle by doing the same thing that I would do normally. I'm going to do some mutual contraction of these guys in pairs and do some expansion. And the structure of that expansion is controlled by superconformal symmetry. And it's going to give me a superconformal block decomposition. I'm going to get a sum over representations of the R symmetry that appear in the tensor product squared of the representations that these guys are in. Of some tensor structures, which are just the projectors from these indices onto that representation. So this is just some invariant tensor of the R symmetry group. Times a function. One function for each of these representations, which is a function of the conformal cross ratios, as usual. So this so far is the same as it would be even if this wasn't an R symmetry. I would have the same structure if it was just a global symmetry. But the key is that the ARs are related for different R in principle. So that's what I get out of supersymmetry. So the problem starts out looking just like a correlation function with global symmetry. I get a small improvement from the fact that R symmetry is better than ordinary global symmetry. But then I really see sort of the structure that's going to dictate how I want to think about this when I ask what these functions look like when I expand them in terms of conformal blocks. And here, there's sort of a binary distinction between some part of the operator product expansion, which involves long operators. By this I mean operators that are in representations of the superconformal algebra that are not BPS in any way. So they're just sort of the generic things. And so they're labeled by the usual annoying data, which might be arbitrary real numbers for the conformal dimensions and whatever their spins are. Plus, you guys probably can't see this. Plus a sum over the BPS part. Where I'm purposefully ignoring all of the details that go into actually knowing what these superconformal blocks look like, but just know that they can be determined by a tedious but concrete calculation if you just figure out the consequences of symmetry. So this is the basic setup that sets the stage for sort of the problem as we view it for addressing the superconformal bootstrap, is that there's all this stuff that looks super familiar. This is ripe for the kinds of numerical analysis that we heard about from David this morning. But then you have all this other stuff, which is the contributions of some nice operators. These are some operators that have conformal dimensions that are integers or half integers. They have some OPE coefficients, which may very likely be non-renormalized in a theory that has a conformal manifold. And it doesn't seem like the kind of stuff where you should have to put a big numerical problem on a computer in order to try to learn something about it. And in fact, I think it's reasonable to imagine that somehow we should be able to just figure all of this out before even worrying about anything numerical. I think that if we're going to really sort of bring the bootstrap to bear on the superconformal field theory problem, you should milk every ounce of sort of niceness of supersymmetry out of the problem first, and then worry about semi-definite programming and hard things like that. So,
but it's not like those terms are any smaller than these, or other special.
No, they're not smaller.
You can't
They
ignore
just
them.
there's hope for these ones. I would say that I'd say that one should definitely feel like there's hope, but at the same time, it's not obvious that you'll be able to make progress. So for theories with conformal manifolds where there's a weak coupling limit, you can imagine being able to do something like fix this at weak coupling, and then maybe there's a non-renormalization theorem that will protect the OPE coefficients, and so that then you'll know the answer. But for theories like the 2-0 theory in 6 dimensions, or like the E6 theories, these isolated theories in 4 dimensions, where would you ever get it? I think it's, you still need to somehow sort of enter sort of honest CFT world to try to get access to this kind of data.
But are there special correlators by choosing special operators at the external legs, which basically get all their contribution just here and not there?
Well, yes, that's the subject. So that will be the subject of my talk. So I would say that until there are, but they're weird. So it's nothing. So hopefully, by the time I've explained the derivation of what these correlators are, it will be clear that it's at least a little bit weird, and it wasn't just something obvious. But at the end of the day, that's what we're going to aim for. We're going to try to get at this piece on its own, but still in the context of some Bootstrap for correlators of local operators. So,
before you go on to that, so to get those conformal blocks, you said it's some laborious procedure.
yeah.
But is there a superspace formalism that you know, just like you could go to an embedding space formalism
Yeah.
and linearize the S, is there some kind of superspace formalism that makes that life easier?
So for some BPS conditions, there's a superspace formalism that David and collaborators explained in a paper from not too long ago. I don't think that there's a coherent story for the most generic shortening condition you could have. But at the very least, you can always go down to components and work out the sort of the word identities component by component if you really need to. Not that I would be able to get the right answer. I need to wait for careful people to have gotten the right answer to use it. But
yeah, you can carry that through to completion for n equals 1 supersymmetry in 4D. And when you go to extended supersymmetry, it gets a little bit more complicated. But there are some situations where you can do it without too much trouble.
Okay, so given that this is the hope, is that somehow this piece of the pie will be accessible on its own, still using the sort of general thinking of the Bootstrap and sort of crossing symmetry. There is a lowbrow and a highbrow way to imagine it working. And of course, the lowbrow way is the way that we actually figured out first, and the highbrow is the way that I want you to think about it. But the lowbrow idea, although when you just say it, it won't be clear that it should be possible, is that from the full set of crossing symmetry equations, you could hope that you can find a decoupled set of equations that refers only to the BPS data. In appropriate cases, this actually turns out to be possible, although I would not have known how to tell you to predict that it should be possible until I've told you the fancier version of the story. But just in full honesty, the only way that we ended up figuring anything out was just by stumbling onto this accident. The slightly more highbrow way of saying what you want to happen is that we want the algebra, sort of the OPE algebra of the full CFT, to truncate. So there's some algebra, a CFT, which is some extremely complicated thing. That's the point of all of this Bootstrap business. And then we want to say that there's some algebra, which is sort of the thing that's being used when you're just probing the BPS data, which is tractable, if you want to make any progress, but still interesting in the sense that you want the constraints of associativity of the OPE to be powerful with respect to this algebra. You don't want to get some just easy to solve associativity conditions that don't actually constrain any of your OPE coefficients or operator dimensions. So the abstract claim that I'll spend the rest of my time sort of slowly making my way towards is that exactly such a truncation is possible in a wide variety of cases, of which I'll sort of focus in on one. So this does happen. So there's sort of two classes of cases where it happens. So it happens for 6-dimensional theories with maximal superconformal symmetry. It happens for 4-dimensional theories with at least half maximal supersymmetry. It happens for 2-dimensional theories with n greater than or equal to 0, 4 supersymmetry. And in all of these cases, this BPS algebra is a chiral algebra. So a meromorphic OPE algebra in 2 dimensions, like we are used to from string theory and whatnot. There's a second set of cases that I will probably not say anything else about afterwards, but I just want to mention it because it's all based on similar tricks, which applies in 3-dimensional theories with n at least 4. It also applies in boundary conformal field theory for 2-dimensional 4, 4 theories. So if you have a half BPS boundary in a 2D 4, 4 theory, then the operator algebra on that boundary has that feature. And also, there are other cases, for example, 4D n equals 4 admits 3D n equals 4 boundary conditions. So this also applies to boundary conformal field theory for 4D n equals 4. Where this BPS algebra is a non-commutative associative algebra. It turns out to actually be a non-commutative deformation of the chiral ring of the theory, which is a highly constrained algebraic structure. But I won't say anything more about that in detail. But both of these stories come from morally the same place. So let me review, probably unnecessarily for many people, the story of where 2-dimensional chiral algebras come from, just because I'll say it in a particular way that makes the rest of the story sort of more obvious what you should do. So chiral algebras usually are a feature of 2-dimensional conformal field theory. Ignoring things about Virasoro symmetry and whatnot, in 2-dimensional conformal field theories, I have an SL2 times SL2 bar global part of the conformal algebra, some generators L plus minus 1 L0, and L bar plus minus 1 L bar 0 that generate the holomorphic and the anti-holomorphic Mobius transformations on the plane. And the chiral algebra of a 2D CFT are those operators so that all the generators of SL2 bar commute with them. So these things are things that are just invariant under the anti-holomorphic part of the conformal algebra. And once that's true, for example, you can see that L bar minus 1, which is just the anti-holomorphic derivatives, are trivial on these things. So the operators that satisfy this are meromorphic objects. So what's normally sort of the complicated OPE algebra now becomes a more tractable looking meromorphic algebra where I only have to worry about meromorphic functions. Where these h's are the eigenvalues of L0. By locality, these operators will be either integer or half-integer dimension, so already have a much nicer life than in a generic operator algebra.
Are these Virasoro or chiral primaries?
So all I've said so far is that these are just these are quasi primaries for the moment. I haven't said anything about Virasoro, and I don't. To get to this point, I don't have to.
Okay.
For the point of view of just saying, there's some meromorphic operator algebra which is nicer than ordinary CFT operator algebras. So, indeed, usually the important feature of the existence of these algebras in 2D CFTs is that they give us symmetry algebras. We do some mode expansion of these operators in some modes, and those have interesting commutation relations, and those give us an infinite dimensional symmetry algebra of the theory. And this leads to the whole story of rational conformal field theory and everything. From my point of view for this talk, that's not the most important feature of these things. Instead, the important feature is that this as an operator algebra itself is much more tractable, and in particular, crossing symmetry for meromorphic operators in 2 dimensions is really easy to study. So, crossing is very tractable for these theories. And that's essentially because of meromorphic. So the correlation function of 4 of these meromorphic operators will be a meromorphic function of the insertion points. And the poles, so a meromorphic function is determined on the plane. So after I've used conformal symmetry to express this in terms of a single cross ratio, I have a function of a single point on CP1. And a meromorphic function on CP1 is entirely determined by its poles. And the poles in this thing is going to be entirely determined by the singular terms that appear in this meromorphic OPE. And so all I need to know is the finite number of singular terms that appear in any one of the contractions of these 4-point function of operators to write down exactly what the 4-point function is. And then, in terms of that finite amount of data, I have some simple crossing symmetry relation, which will tell me that this is f of z, where z is the conformal cross ratio. This will give me some relation where f of z is equal to so if these were operators of dimension 1, then this prefactor would be right. And in more general cases, there's some other prefactor. But it's some simple prefactor that you can work out. And this gives you just a totally easy to write down condition on the various OPE coefficients that appeared in this thing. And then you can just figure out if crossing symmetry is obeyed or what sorts of constraints it imposes.
So the reason this is a finite amount of data is an assumption that there's kind of that you only have a finite number of operators with dimension on the smaller than some bound, or
well, so for a given conformal dimension for I and j, there can only be a finite number of terms. There can only be a finite number of different poles.
And right? That's from localities, from that because.
Oh, okay. So I'm using some unitarity. The conformal dimensions I'm going to take to be positive.
Mm-hmm.
So the most singular term I can get is just 1 over z minus w to the sum of the conformal dimensions.
I'm just asking why I couldn't still have an infinite number of operators on the right-hand side.
Well,
I just have a continuum, say, of dimensions of.
Well, you can't have yeah. By locality, you only get
So that's
you only get ordinary.
You only have.
Yeah, you only have integer powers up here, and these guys are either integer or half integer dimension.
These are guys with the dimension equals the spin. Right.
That's right. These guys. So these guys obey
H tilde is
obey
0.
L0 bar is equal to 0, which is equal to H. Well, whichever one. So they're conformal, and then L0 is equal to H minus L2. So the difference is just the spin. So integrality of or half integrality of the dimensions is just determined by, well, okay, I could be doing some weird parafermion thing, but I don't want to worry about that. I want to worry about nice cases. So my claim is that for a single sort of meromorphic 4-point function, the crossing symmetry problem is very tractable. I might not find that all the OPE coefficients are determined, but it's at least sort of something I can write down on a single piece of paper. In the nicest class of chiral algebras, the whole thing is sort of a finite dimensional problem, where nice cases are what people call W algebras. So in the case of W algebra is a chiral algebra where the spectrum chiral operators is finitely generated in the sense that there's some finite set of these OIs, so that if I take normal ordered products of those guys and their derivatives, then I get everything. And many of our favorite chiral algebras are W algebras, although it's sort of an abusive terminology to call like the Virasoro algebra a W algebra. But for this definition, it is. The Virasoro algebra just has T as its generator and the normal ordered products of that. Similarly, affine current algebras are W algebras in this sense because you just have the J's. And if this is the case, if you know for some reason that you only need to worry about a finite set of generators, then you only need to worry about solving. Then sort of all the data is contained in the singular OPEs of those finitely many generators with each other. So you end up with a finite amount of data determining all the correlators, and then you solve all the crossing symmetry equations for all the 4-point functions between the generators, and you're done. Or maybe there's no solution, and you turned out to have postulated a W algebra that didn't exist.
So just to make sure I understand, this says that you have a closed subset of these chiral operators such that it's only the guys that appear in the singular terms on the right-hand side are that set.
Or normal ordered products and derivatives and everything. So it doesn't just have to be the set. So you can have, for example, in the Zamolodchikov W3 algebra, the famous one, you have some dimension 3 operator that has sort of a TT guy on the right-hand side. But because this is built in terms of the stress tensor, you're not introducing any new different singular OPEs because the singular OPEs with composites is determined in terms of the generators.
So it's not Lie algebras.
It's not a Lie, well, it's either a Lie algebra with a lot of non-linear relations that you can impose, or it's not a Lie algebra. But from the point of view of, I mean, if you don't try to do the mode expansion and you just play with these 4-point functions, then everything stays reasonable looking.
So the normal ordered products then are just things that appear in other OPEs, but they're not a singular term, but they don't vanish when they.
That's right.
come
That's right.
together. So
The
it's
conformal
just-
normal ordering means just subtracting
Yeah,
off the
singular.
singular pieces. So this is a structure which is extremely rigid. So in practice, if you actually go out and start speculating that you might have a W algebra with some selection of generators that you drew out of a hat, and you wrote down the most general singular OPEs you could, and then you started trying to solve crossing symmetry, you would actually find no solution. Sort of generic things pulled out of a hat won't work. And when things do work, you usually have one or a couple of parameters. You don't find like huge spaces of parameters of the solutions of crossing symmetry. So just as sort of as a non-precise, wishy-washy statement, these things are very rigid, and if you end up with them, you don't have much freedom. Couplings are pretty much fixed. And I'll just claim that this nice version of chiral algebras, which are W algebras, turn out to be the case in the preponderance of examples that we've been able to understand in this whole 40, 60, etc. story. Although I can't tell you why it should always be the case.
So what are the not nice cases?
Oh, well, this condition just doesn't have to be true, this finite generatedness condition.
Yeah.
So you could have
There's no set
the
that
spectrum of
closes in
the
that.
spectrum of operators could just keep each time you add a new generator, then you There's some set of states that now exist from all the composites you can build, but there can always be more and more and
So
more.
when people talk about W infinity algebras,
W infinity
those
algebras are a
nice
little bit
cases or
tricky.
not nice cases?
They're sort of a limit of nice cases.
Yeah.
Those usually come up when you have a family of nice cases with increasing numbers of generators. And so you can get to infinity while it being sort of controlled. Whereas if you just took like a totally out of nowhere thing that turned out to not be a W algebra, it would be, you wouldn't necessarily have the same degree of control.
But by the time you go to W infinity, I guess you get back a Lie algebra,
Not always.
you know?
Sometimes you frequently have some. So for example, in this,
W
there's this.
infinity and W1 plus infinity and all that stuff.
Yeah. So the difference. So there's a W infinity, W1 plus infinity, but those guys. Well. Sometimes you get Lie algebras back up, but not always. You can actually get to W infinity, something like W infinity in different ways, and where you do like double scaling limits, where you take the n of Wn to infinity, but you take a central charge to infinity at the same time and keep some ratio constant, and you can keep nonlinear terms. Okay, so now I've claimed that there's this sort of maximally nice algebraic structure that can exist in 2D CFTs, which is tractable if you get lucky enough. And I've claimed that it's going to come from somewhere in theories that live in more dimensions that don't naturally have this property. So where does that come from? Well, to give the answer, I'm going to just talk about something else for a little while, after which it will become more clear how I should go about finding this. If my stated goal is now to find such a structure in some truncation of theories with a lot of supersymmetry and more dimensions, I'm going to work my way up to it. So, I'm going to offer a brief interlude on a subject which is probably familiar to many people, which is chiral rings. Don't be annoyed by the abuse of the word chiral. This is n equals 1 theories in 4 dimensions. This is just the usual version of chiral, not some chiral algebra thing. So in n equals 1 theories in 4 dimensions, I have a superalgebra which involves these supercharges that anti-commute to give me the momentum generators, so the translation generators. And I have chiral ring operators which are operators which say commute with one of the sets of supercharges, either the q's or the q tildes. And the nice thing about chiral ring operators is that they obey a simplified algebraic structure because of the fact that they're annihilated by the action of one of the supercharges. So in particular, what we usually say is that because q alpha is equal to 0, so q squares to 0, it gives us some differential that acts on the Hilbert space of the theory. Or alternatively, I can define cohomology classes with respect to that supercharge, which means I take these operators that are annihilated by the q, and I think of them as being defined up to the addition of something that is q exact. So adding something that is q exact preserves this property because q squared is to 0. So the q acting on the second guy is automatically 0. And working at the level of these equivalence classes is legal from the point of view of the algebra. So if I take 2 equivalence classes and I multiply them together, then the operator I get out will be well defined at the level of this equivalence relation. And the algebra that I get at the level of these equivalence classes has a nice property, which is that the derivative of one of these equivalence classes is equal to 0, because the derivative is q of something. So acting with a derivative on this thing gives me q of something, which is 0 at the level of this cohomology.
You think of these equivalence classes like conformal blocks. I mean not conformal. I mean like primaries plus descendants under the super conformal descendants.
Yeah, you can think that so within a given conformal family,
Right.
you could have at most sort of the usual derivative descendants you can add those and stay in the same.
Right.
Stay in the same class.
Right.
But this actually doesn't depend on
is-
any conformal field theory.
Yeah,
This is just
yeah.
true in Poincare supersymmetry.
I'm just trying to map this into, yeah.
But now I just want to, so this was a super fast review, and I apologize if it was too fast. But all I wanted to do was have the opportunity to reword what is going on here in a suggestive way, which is that by passing to the cohomology of a certain no-potent supercharge, I have changed the space-time transformation properties of these operators. These operators originally were in a non-trivial representation of the space-time translation group. If I wanted to move them around, I would act with derivatives, and that would be non-trivial. But now, because the space-time symmetry I cared about was Q-exact, at the level of cohomology, I've gotten objects which are in the trivial representation of the space-time translation group. So, by saying this familiar thing in that language, I've sort of set up exactly what I need to do in order to reproduce the success of two-dimensional chiral algebras in the context of supersymmetric theories. So in this case, the thing that mattered was having operators that with respect to the SL2 times SL2 bar on a plane were invariant under the SL2 bar. So in a general case, in higher dimensions, let me imagine picking a two-dimensional plane inside of my d-dimensional space just by hand. There will be an SL2 times SL2 bar subalgebra of the conformal algebra in d dimensions that acts just as the usual holomorphic and anti-holomorphic Mobius transformations on that plane. And now, my project is to pick some fermionic generator, which I'll call with a funny square q, in the superconformal algebra. At the moment, I don't know what superconformal algebra will be yet, but whatever my superconformal algebra is, I want to pick a q that has the properties that it squares to 0, so it's legal to work at the level of cohomology. That it commutes with the generators of the holomorphic SL2, because at the end of the day, I want something that looks covariant with respect to the holomorphic SL2 on the plane. And for which Q, acting on something, gives me the SL2 bar generators. If I can do this, if I can just go and analyze superconformal algebras and find this structure, then I'll be finished. Morally finished, because I will just be able to repeat the words that I use in the chiral ring case to discover that by studying operators that are in the cohomology of this supercharge, I get the algebraic structure of the chiral algebra. This is actually not possible. There is no such a Q in any of the superconformal algebras that I know about, which is, I think, all of them. But there's a trick, which I'm forced to do, which works, which is to not have the SL2 bar, not have the antiholomorphic Mobius transformations be Q exact, but have the diagonal subgroup of SL2 bar with the complexification of an SU2R symmetry, as in the superconformal algebra. If I allow myself to have this additional twist, then this is possible. And in fact, such a Q exists in precisely the cases that I probably erased that were of type 1. So the 6-dimensional 2-0 algebra, the 4D n equals 2 algebra, and the 2D 0-4 algebra all have such a supercharge. And schematically speaking, it always has the structure of the combination of a Poincare supercharge and a special conformal supercharge. So I wanted to claim that once I've identified this fact about superconformal algebras, that I can sort of tentatively declare victory. That would be a tiny bit premature, because it's important that the cohomology not be empty. There need to be operators which are annihilated by this supercharge, which are not Q of something. Fortunately, it's not empty. And to describe the operators that give me well-defined Q cohomology classes, there's sort of a natural two-step procedure. The first thing to do is to look at operators at the origin in this R2. And there, it turns out that you can just sort of do some Lie algebra and figure out that an operator at the origin will give me a non-trivial cohomology class if it has delta minus L over 2 equals R. So L is the rotation generator in this plane, and R is the cartan of whichever SL2 it was that I twisted. And so from now on, just for the sake of convenience, I'll have in mind the 4-dimensional n equals 2 case, where there's no ambiguity about what the SU2 R symmetry is. And there are many operators that have this property. So you can go and look at some paper where Dolan and Osborne have classified all the representations of the n equals 2 superconformal algebra, and you find a whole list. In Lagrangian theories, this involves the so-called Higgs branch chiral ring operators, which are built out of the quark scalars, the q's and the q tildes. It also includes a bunch of wacky representations that have names like C hat and D, and it's not particularly illuminating to have me say the names. But it's a reasonably big list, but it's not comprehensive. There are also many kinds of BPS operators that do not have this property. So we are limiting our scope by saying that we're gonna work with these guys. So let me call this condition
For the
star.
topological gauge theories where you twist by the R symmetry, are they related to this construction at all?
I don't think so. In a second, you're going to see why.
Okay.
Maybe you'll see why. In a second, I'll say something, and then we can discuss it again. Which is the question of how this twist is really working. So the twist really comes into play when I want to take an operator and put it somewhere than the origin in this space. So notice that the translation generators don't commute with the S's. So if an operator is at the origin and I just move it away from the origin naively, it's not going to stay in the cohomology of Q. It's not going to stay Q closed. That's not a surprise because I was forced to do this thing. I was forced to introduce this funny hatted SL2, which in particular includes a hatted L minus 1 bar. This is L minus 1 bar plus the lowering operator of the SU2R that I twisted by. So the thing, the thing I'm supposed to do in order to behave nicely with respect to this Q is not use L bar minus 1, but use L hat minus 1, which means that an operator at some point ZZ bar should actually be constructed by conjugating it with this hatted thing. This is sort of a funny thing to do. We can write it in a slightly less obscure way if I just pick an operator which has some definite, that lives in some definite representation of SU2R. So let me imagine that O0 is some O plus plus plus, etc., where these are two-component SU2R indices. So this is some guy in the highest weight state of his SU2R representation. What this tells me to do, if I expand it out, notice that the lowering operator, R minus, is actually nilpotent. If I act on this guy too many times with it, I'll get 0. So I can expand out the exponential and truncate at a finite number of terms. So this thing I get at some other point is equal to etc. So this is in some sense, staring at this is the reason that I said that there's a way to choose the operators appropriately to focus on this BPS algebra, but it's weird and not obvious. The way to get correlation functions that sort of access this BPS truncation of the algebra is to make sure that an operator that I put in at some point is this particular space-dependent linear combination of its different R symmetry components. So depending on what point it is at in the plane, I need these coefficients to be the appropriate values. So this is sort of my answer to your question, is that this is not the kind of thing that I normally have to do to move operators around in a topologically twisted theory. And even though this looks weird, there's actually something great about this funny rule, which is that it overcomes a problem that I didn't mention before, which is that normally when one plays these Q cohomology games, in particular something like the n=1 Cairo ring, the operators that give me Q cohomology classes have definite signs for their R charges. And that means that if I wanted to find correlation functions of operators that are in cohomology classes, they're all 0 by R symmetry selection rules. So for example, in n=1 SCFT, there are no non-zero correlation functions of Cairo ring operators. Here, this guy who's the highest weight state is sort of the guy that naively looks like a Cairo ring operator. But because I've had to add all the lower components, now if I put 4 of these guys at some random points on the plane, I can get a non-zero correlator. This is how I get some interesting structure in the actual correlation functions, and I get to impose crossing symmetry.
So going back to Al's twisting question, doesn't the L hat look like I'm turning on some background spin connection? So maybe I'm twisting, but
It's not the
Yeah,
usual
yeah,
twist.
it does look like that. You're turning on a constant background gauge field, which is non-unitary. So you're turning on a z bar in these coordinates, where z and z bar are in the place, is equal to this. And that sort of parallel translation with respect to that background gauge field tells you to do this. So in that sense, it's twisting. So it's legal to use the word
Right,
twist.
right.
It just doesn't look like
It's not equal to
familiar
spin connection or
things.
anything like that. It's just
yeah.
Yeah, it's because it's in flat space.
right.
So, when did I start? 3 or 3:30?
You started at 3:30.
Oh, okay. So let's do a quick example, just to see in some extremely sort of stupid-looking way how it is that this rule sort of performs something of a miracle that I want it to perform. So there's only a few theories where I know how to do computations completely explicitly, and they're free theories. So let me consider a free hyper in 4D. In the theory of a free hypermultiplet, I have some scalars, which are R-symmetry doublets, which are sort of related to each other in this way. And these are operators of dimension 1, spin 0, and their highest weight states are R equals a half. So these obey condition star from the other board. So these just the Q and Q tilde themselves are good for playing this game. So what am I instructed to do? There's some operator which is involved in this BPS algebra, which is constructed in this way that's supposed to live in the plane and look like Q of Z is equal to, maybe I should call it Q of Z equals Q of Z bar plus Z bar Q tilde star of Z bar. And if I really want to be pedantic, I'm considering these guys modulo Q exact things, so I'll have this little square bracket. So these are weird position-dependent things, but now I can take their OPE if I want to. And I can do everything explicitly because it's just free fields, so I know how to do free field width contractions. And if I do it, and for the moment let me only worry about singular terms, then I get singular terms from when Q tilde hits Q tilde star, and when Q hits Q star. Both of those guys give me 1 over Z minus W squared, but I get an explicit Z bar minus W bar upstairs from these prefactors. So I've just done some ridiculous thing where I just canceled the terms out by hand and ended up with something meromorphic. This makes it look like I just got lucky and you could play the game with free fields and great, you made something stupid work, but in some interacting theory, why should anything work? And that's what the whole cohomology technology guarantees for you. This same miracle is just going to occur every time you want to do this in some arbitrarily complicated interacting theory.
What did we need other than just an SL2R R symmetry, SL2R symmetry in order to have this work?
Right. So I can tell you the irreducible. I don't want to make a totally authoritative math statement because there could be tweaks which actually abandon some things. But in all the cases where it works, what you have is, I'll just say it out loud. What you have is an SU1, 1/2 superconformal algebra that supersymmetrizes the antiholomorphic SL2. So in any given superconformal algebra, you can ask what sort of the supersymmetrizations are that are available for a given antiholomorphic Mobius part of the conformal algebra, and it may or may not include an SU1, 1/2. Sometimes you get like weird OSP things instead of that particular thing. And in order for all the details to work, that's what you need. And actually, it's still SU1, 1/2 in this three-dimensional case that I mentioned that I'm not talking about. In that case, instead of being the antiholomorphic transformations on a plane, it's just the transformations on a line, just the SL2R that acts as the one-dimensional conformal group on a line. And if you have an SU1, 1/2 supersymmetrization of that, then you get this non-commutative associative structure.
So you did say that in 2D the chiral rings have no correlation functions, only in higher D that you're trying to find correlation functions of chiral ring operators.
Well, in conformal field theories, in superconformal field theories, if I just take a correlation function of chiral ring operators by the usual definition,
It's always.
I'm always out of luck because of our symmetry selection rules.
But this trick of making
This trick means that I'm not just working with the chiral ring operator. I get this twisted translation that
But you can
means
do this in 2D also.
you can do it in 2D if you have 0, 4 supersymmetry. You need this non-abelian part of the R symmetry to do the trick for you. So if it's just 0, 2 or something, then you can't do it. And just for fun, let me mention that if I just give these guys new names, like beta and gamma, then this is the OPE that defines a free beta gamma system of dimension 1/2, 1/2. And all I did was use these individual operators, but you can commit yourself that in the free hyper theory, all of the operators that obey dimension star can then be expressed as the normal ordered products of these guys and their holomorphic derivatives. So the whole structure, the whole algebraic structure is exactly the beta gamma system of dimension 1/2, 1/2. Which is, all right, we should have expected something free, so what else would it be? Without writing it out in the same way, I'll just mention that you can, of course, so free theories you can do explicitly. So you can do the rest of the free theories. So the other free theory that I know in 4 dimensions is the free vector. And in the free vector theory, the operators that obey this condition are the positive helicities of the top components of the R symmetry doublets of the gauginos. And after you play the same game and do things out explicitly, then you end up with, well, let me just say that you should call this guy B, and you should call this guy DC, and you get the OPE algebra of a BC ghost system. At dimension 1, 0. All right, so that's the other free theory. So you got the other free theory. And the third free theory is the free tensor multiplet in 6 dimensions. And in that theory, I haven't told you, but there's some particular part of the R symmetry which is the right one to give you this thing. So the R symmetry of the 2-0 superconformal algebra is SO5, and the relevant SU2 subgroup is sort of the 3x3 matrices inside of the 5x5 matrices that I guess people sometimes call the vector subgroup. So you can play the game, and in this case, it's the free tensor itself, its highest weight state. So this is some scalar. The highest weight that lives in the 14 of SO5. And you can do everything by hand again, and it's not very tedious. But at the end of the day, you should name this guy J, and you get the OPE of a U1 affine current. So that exhausts some free theories that give you free theories, and everything works very nicely, but they're all free, so who cares? In general, this is some abstract structure that has to hold, but I still need to generate some tools to actually figure out how to analyze it for interacting theories, especially weird interacting theories that are my stated goal, things like the 2-0 theory and E6 theories and things. And we don't really have a science yet. It's not, or I guess, the guy who wrote the convex optimization book likes to talk about whether things are technologies or not, based on whether you can use them without thinking. So we don't have a technology yet for generating the chiral algebras of arbitrary, complicated interacting theories. You still have to sort of push and shove and guess. But there are some general features that help you get started if you're going to play some sort of quasi-guessing, educated guessing game. So the general features correspond to general features of four-dimensional, let me now restrict to four-dimensional theories again. General features of four-dimensional SCFTs. So, as we said before, it's normal to expect that I'll have a stress tensor most of the time, if this is some local theory. A stress tensor doesn't satisfy condition star, but as I said at the beginning, the great thing about supersymmetry is that there are other operators in the same multiplet that morally know that they're part of a stress tensor multiplet. So it turns out that the plus dot component, the sort of positive helicity, most positive helicity component of the SU2R current, which is in the same supermultiplet as the stress tensor, does obey that condition. So just the fact that I get a stress tensor in my theory guarantees this particular operator that's going to play a role in the chiral algebra. So this is like some guy with delta equals 3, L equals 1, R equals 1, and you can check. So there's going to be some operator in the chiral algebra that comes from building this twisted thing and treating it as a cohomology class. Something that you can immediately check is that with respect to this residual holomorphic SL2 acting in the plane, this guy has dimension 2. And luckily, the OPE of this thing with itself is strongly constrained by ward identities. So it's constrained by SU2R ward identities, and also by superconformal ward identities that relate it to the OP of the stress tensor with itself. So you can actually work out all of the relevant terms in the OPE of this operator with itself that can be involved after I pass to the Q cohomology. And let me, as usual, just tell you the answer by telling you what your name for this thing should be. It should be called T, because this thing has a singular OPE with itself. It looks like this, which is, of course, the singular OPE of a stress tensor in a 2D CFT that generates the Virasoro algebra, where the Virasoro central charge is related to the C central charge of the four-dimensional theory by a factor of -12. So this thing will generate a negative central charge Virasoro.
Is this a statement that it must contain those terms on the right-hand side, and that there can be no other?
There can be no other. There can be no other Q closed, not Q exact terms that are singular.
Right.
So this is it's always
yeah.
Okay, so that's gratifying. I started out with a stress tensor. I sort of shuffled over a little bit to use a nearby operator in the same supermultiplet, but it handed me a stress tensor back. So that's nice. Sort of stress tensors give me stress tensors.
So the A central charge doesn't show up anywhere?
Doesn't play a role
It just
anywhere.
drops out completely.
Completely absent. Another.
What do we think supposed to think about the sign change of the central charge from?
I don't know. What do you think about it?
Well,
Like
so there was
ghosts.
no reason to think that this kind of 2D type chiral algebra should be unitary. Just
Yeah,
it's not embedded in any.
that's right. In fact, the passage to the cohomology of this supercharge really, it breaks everything in some sense. So in this particular case, right, so here you have some t. And normally in a 2D CFT you say, all right, the stress tensor is some real operator, and its two-point function with itself should be real and positive if it's going to be a unitary looking theory. But now we can go back and compare to what sort of I should have tested for unitarity in 4 dimensions. And in 4 dimensions, I should have taken J minus minus dot. And that guy doesn't live in the cohomology at all. So I've sort of broken, I've really broken sort of the Hilbert space structure on the original theory and ended up with some new thing that's going to have a new notion of conjugation and new reality conditions and everything.
It's just like how when you twist, you lower the central charge sometimes down to 0. This is sort of because twisting made it negative.
Well, this is somehow more abstruse. So normally, when you twist and change the central charge, you're usually redefining the stress tensor of your original theory, right? You define a stress tensor by some dj or something. Here, you're just looking at some totally other operator, and you're calling it t because it has the Virasoro OPE. But from the point of view of your original nice unitary CFT, it's just not that. The other general feature that I mentioned at the beginning of my talk is a lot of times, if I don't know anything else, I might know if my theory has some global symmetry. So in particular, if there's some conserved currents associated with the global symmetry. And again, the conserved current itself does not satisfy this condition star. But again, there's another operator in the same supermultiplet that does. In particular, J mu A is schematically equal to Q squared acting on some scalar operator, which is sometimes called the moment map operator. This is a certain chiral ring operator in n=2 theories, where this operator itself has dimension 2. It's a spin 0 and an R symmetry triplet. So that does obey condition star.
So mu on the right's the name of the operator.
Sorry, that's really confusing. Let me just call it M for now. Although I usually call it yeah, this is the thing that plays the role of the moment map for the action of the G symmetry on the Higgs branch. And so there will be some operator that I get by doing this twisted construction. And again, I can go and try to look at the OPE and figure out how much of it I can determine using word identities. In this case, I'm really using supersymmetry even more heavily than in the other case, because the thing I'm going to use is that the OPE of this thing is constrained in terms of the OPE of the conserved current with itself, which is constrained by G symmetry. And you will not be surprised to have me tell you to call it JA. Oh, I should have said that this thing has holomorphic dimension 1, and the OPE looks like the OPE of, let's see, minus K over 2 So this looks like an affine current algebra, where the level of the affine current algebra is equal to -1/2 times this K that is defined in 4 dimensions, the so-called flavor central charge, which tells you about the norm of the canonically normalized flavor symmetry current. So we've got this sort of as above, so below construction again, where sort of the current doesn't get to make it itself, but it's responsible for its friend that comes down and turns into a current again and gives us the same kind of symmetry. I won't write it down on the board, but a very special case, which is another sort of general feature, so to speak, is that in the n=4 theory in 4 dimensions, which is a special example of an n=2 theory, one of the general features is that it has n=4 supersymmetry, so it has extra supercurrents involved. And so you have some extra operators in those supercurrents. And you get exactly the same story, where the supercurrent itself doesn't obey the right condition, it has a superpartner that does, and after you turn the crank, you end up with something that acts like a supercharge in a two-dimensional chiral theory, some dimension 3/2 supercharge. Okay. So, where are we?
I guess you could also write down a formula relating FABC to the 4D current 3-point function coefficients.
Yeah, that's that FABC is the structure constants of the same. So the same structure
It's
constants.
the exact same. It's the exact same.
Yeah, it's the exact same.
And if you had a central extension of the superalgebra, of the original 4D superalgebra, would your constructed superalgebra also be centrally extended with a minus of the z?
What kind of central extension are you?
Well, for example, like in the presence of a soliton or something, you get a central extension.
Oh, I don't know.
Okay.
Okay, so from here, there are 3 directions that one can go, and I'm not going to go in all of them, but I'm going to mention them. I'll write them up, and then I'll decide which one to do. So one direction is to take this structure and start figuring out what one can do via guesswork. So there are more features of the dictionary that I'm not going to have time to explore in detail. But for example, the spectrum of operators in these chiral algebras is what's counted by certain limits of the superconformal index of these theories, on which there's been a fair amount of work. So frequently, one can go look up some smart person's paper where they computed a superconformal index and figure out if it looks like the character of some reasonable looking W algebra that satisfies some of these basic consistency conditions. And then if it does, you can go and guess that it's a W algebra and try to solve the W algebra crossing symmetry problem. And this is a way to try to get at reasonable conjectures for the whole chiral. This is if your game is going to be, I want to know how to say once and for all what the whole chiral algebra is that's associated to a given theory. That's one kind of problem you can work on. Take your favorite theory and figure out if you can come up with a plausible guess, and even check some features of that guess for what the chiral algebra is. A second thing you can do is use subalgebras, of the chiral algebra to set up the non-BPS Bootstrap. So for these special cases I was just talking about, I know exactly what the 4-point function of chiral of these currents is. This OP is fixed, and so for that 4-point function, I can just write down the chiral algebra 4-point function. Similarly for the stress tensor, I know what the 4-point function of stress tensors in 2 dimensions is, just based on knowing the central charge. So that gives me some chiral algebra 4-point function, and it turns out that if I have I have the chiral algebra 4-point function, that allows me to fix the BPS data in the corresponding non-chiral 4-point function. So for example, in this moment map case, I had these moment maps. I had to take these particular twisted combinations of them in order to get this chiral algebra structure itself. But once I have it, I can go back and study the honest-to-God 4-point function of the moment maps without any of that specialization. And all of the BPS operators that contribute to the superconformal block decomposition have their data encoded in this chiral algebra piece of it. So I'm able to go back and then really feel good about getting into numerics, because I'm not going to be missing something that I could have solved by hand. And then 3 is, well, it's not totally unrelated to 1, but it's just there's more to say, and also probably more to understand, about how various things that you can do in 4 dimensions manifest themselves at the level of the chiral algebra. So just to mention a couple of things, a standard task that I am likely to perform if I'm studying 4-dimensional CFTs is to take a CFT with some global symmetry and gauge it if the gauging will preserve conformal invariance. And that turns out to be the case when this flavor central charge of the corresponding symmetry that I want to gauge is equal to 4 times the dual Coxeter number of the group. So if this condition is true, then I can take some CFT, this 4D n equals 2 CFT with a global symmetry, and gauge it and end up with some new CFT. So something I would like to be able to do is say, at the level of the chiral algebra, if I knew a chiral algebra that was associated to the original ungauged theory, what does gauging do? And a priori, I wasn't entitled to have an elegant answer. I mean, it could have just been a situation where you had to go back and remember that you were studying a 4-dimensional theory and work hard and then sort of solve the problem all over again. But luckily, there is an elegant explanation. There's a certain sense in which 4D gauging is equal to 2D gauging, again with the above-below thing. More specifically, precisely when K4D is equal to this thing, this means that K2D is equal to minus 2 times the dual Coxeter number of the relation I had before. Precisely when I have a current algebra at level minus 2h check, I can build a nilpotent BRST operator in the chiral algebra, whose cohomology is the chiral algebra of the gauge theory. And you can actually sort of dig into it and figure out the inner workings. And what's happening is by taking that BRST cohomology, you're encoding the one-loop correction to the supercharges that sort of takes operators that were BPS before you gauged and recombines them and lifts them out of the spectrum. But you can forget about, once you know the rule, you can forget about that story, and you can just study it at the level of the BRST problem. And knowing how to gauge is helpful if you want to start guessing things. Because if, for example, I want to guess what the rank 1 E6 chiral algebra is, something that I better do is if I gauge it to a free hypermultiplet, I better get the same thing that I got out of SU3 superconformal QCD. So I listed those 3 things, and now I'm out of time. So let me finish with just a list of a handful of interesting theories where we think we actually know how to characterize what the chiral algebra is. And in these cases, what's contained in that, if you know what the chiral algebra is, then you know an infinite number of 3-point functions of BPS operators, which in the case of something like the 2-0 theory, I'm not sure how else you would get. And it also means that you can start setting up the numerical bootstrap. So let's start at the top. we think we know the answer for the 6220 theories of type G, where G is some simply laced the algebra. You get the W algebra of type G, which is the same W algebra, it should be noted, that appears in the HET correspondence with some connection to these 2 zero theories. So it's hard not to think that there's a connection between this whole story and the AGT correspondence, although it turns out to be harder to make the connection than you might expect. If you take the rank 1 E6, E7, and E8 Minahan-Nemeshansky theories, then it appears that the chiral algebra is just the affine current algebra at the appropriate level. And nothing else. And this is actually a general, this appears to be a general feature of the rank 1 theories, that their chiral algebra is just their, just the affine version of their flavor symmetries with nothing else. So this is also apparently true for SU2, superconformal QCD, which is the SO8 theory. And that appears to be all there is. So you can check these things, for example, at the level of the superconformal index, and by doing these gauging tricks to see if they behave correctly with respect to S-duality.
For other ones, like the C5 theory, these.
I don't know about the C5 theory.
So,
as Mario knows.
So there are other rank 1 theories
so
that have been found by S-duality. One, for instance.
Sorry, I was being too broad. Well, this is still true. The words I was saying were being too broad. What I should have said was the rank 1 F-theory singularities. So the theories that come from a single D3 brane probing an F-theory singularity. Those are the ones for which the statement that it's just the affine current algebra appears to be true. Not, it was too broad to say all of rank 1. N equals 4 gives you some super W algebra that's hard to describe.
What did you need to know to? Well,
in these cases, the main thing that led us to the guess was the superconformal index. It's not a proof. The index can have cancellations, so you don't know the character if you know the index, but it's a little bit hard to believe. I mean, there would really need to be a conspiracy against you.
But let's say you didn't know the index, but just knew various S-dual descriptions of them, and so you can use your gauging information. Would that be enough to give strong evidence? You don't know? I don't know.
Oh, you're... Sorry. I understand what you're saying now. Yes, that would be enough to give strong evidence. Okay. There's sort of a meta bootstrap question, which is whether you can use this whole S-duality web of class S in order to sort of theory space bootstrap the chiral algebras by using this generalized associativity from S-duality. And I don't know if it's possible, but it's tempting. For the superconformal index, Leonardo Rastelli and Davide Gaiotto and Shlomo Razamat were able to sort of bootstrap the index using that. So it feels like maybe you should be able to lift that up. But
so these other rank 1s that I was mentioning, a bunch of them at least are in class S, and so you could.
Yeah, there's definitely tools. There's also the Higgsing, the thing that shrinks the punctures.
Right.
There's also a BRST prescription at the level of the chiral algebra that takes a theory with one puncture and hands you the theory with a smaller puncture. So there's a lot of consistency checks within the class S framework to any conjecture that you might have. Well, I think I should be done. Thanks for listening, and also thanks again to the organizers for putting together